Cauchy's integration using Jordan's lemma, assignment 7. Here are some remarks which are very useful. First is cos hyperbolic a is equal to e the power a plus e the power negative a over 2. Sin hyperbolic a is equal to e the power a minus e the power negative a over 2. Then is sine of iota x is equal to iota sine hyperbolic x, and cos iota x is equal to cos hyperbolic x, and then e the power x is equal to cos hyperbolic x plus sine hyperbolic x, and e the power negative x is equal to cos hyperbolic x minus sine hyperbolic x. I am going to use these remarks in the following example. So the example is, prove that integration from 0 to infinity cos of ax over x square plus a square dx is equal to pi by 4 cos hyperbolic a minus sine hyperbolic a into e the power negative a, where a is strictly positive. This I need to prove. We will integrate fz is equal to, yes, in the numerator I am having cos of ax, right? So I need to change the numerator in e the power iota mz. Now here m is equal to a. So the numerator becomes e the power iota az over, this will be z square plus a square. So we will integrate this function fz along the contour c, and c is contour along the real axis minus r to positive r followed by a semicircle tau, right? Now first one is you have to find out the poles. So taking the denominator equal to 0, I get z is equal to, yes, what is this, plus minus 2 iota, of which only z equal to 2 iota lies inside the contour, the positive one. And then I need to find the residue at z equal to 2 iota. And the formula for that residue is equal to numerator as it is divided by derivative of the denominator with respect to z. So this becomes 2z at z equal to 2 iota. So this is equal to e the power iota az over 2z at z equal to 2 iota, which becomes, now z is equal to 2 iota, that is negative 2a. So e the power negative 2a over 4 iota. Very fine. Third step is, by Cauchy's residue theorem, the integration along the contour fz dz is equal to 2 pi iota times the residue. So it is 2 pi iota times the residue is e the power negative 2a over 4 iota. So iota iota cancelled out. Again this 2 is also cancelled out with 4, and the remaining term will be pi by 2 e the power negative 2a. Very fine. Alright. Now this contour C will split up into two parts. One is from negative r to positive r along the real axis. So there the function will change into x variable, plus the integration along the tau, semicircle tau, fz dz. This is equal to pi by 2 e the power minus 2a. Now I have to apply the Jordan's lemma over here. That is obvious that the second integral will always tending to 0 when r is tending to infinity, right? So by Jordan's lemma we get, as r is tending to infinity, this integration will be equal to 0. So letting r tends to infinity in 1. So minus r to plus r will become now minus infinity to plus infinity, right? So this is equal to then pi by 2 e the power negative 2a. Now because I need cos in the numerator according to the given example, I need cos in the numerator. For that I have to equate, yes, very good, real parts, very good. So equating the real parts, we get minus infinity to infinity, this becomes cos of ax, this is what we need, and this is x square plus 4 dx. This is equal to, alright, this is pi by 2. This is already your real part. There is no iota, so this will be as it is. Okay, can I write e the power negative 2a as e the power negative a into e the power negative a? There is a reason for that. This implies, now this integration, because this is your even function, cos is even function and denominator is also an even function, so this integration will change into 0 to infinity twice. Cos of ax over x square plus 4 dx is equal to pi by 2. Okay, instead of e the power negative a, I'm using the first one and writing second one as it is. I don't need this. Okay, the e the power negative a can be written as, I know that cos of hyperbolic a is equal to e the power a plus e the power negative a over 2, as according to the remarks. And then sine hyperbolic a is e the power a minus e the power negative a over 2. If I subtract these two, I will get this e the power a by 2 will cancel with e the power a by 2. So if I subtract these two, I will get e the power negative a. Simple. So instead of e the power negative a, I'm writing cos hyperbolic a minus sine hyperbolic a. This is what we need. Yes, very good. Alright, now this 2 will come in the denominator to the other side. So 0 to infinity cos of ax over x square plus 4 dx is equal to pi by 4 cos hyperbolic a minus sine hyperbolic a into e the power negative a. Fine. So here ends up the solution. Very easy, just 4 steps. Find out the poles, then calculate the residue at the point which lies inside the contour. Use the Cauchy residue theorem, and fourth one is use the Jordan's lemma and then equate whatever part you need to equate, real or imaginary. You will get your then final result. Step-by-step solution it is, right? Okay, so this is I'm giving you an exercise. Prove that integration from 0 to infinity cos of ax over x square plus a square dx is equal to pi by 2 e the power negative a. Very similar to the previous example, and a is strictly positive over here. Hint is given to you, find out the poles, then residue is also given to you, check that, and then equate the real parts. Why? Because there is cos in the numerator. Fine. Thank you so much for watching this video. Alright, have a blessed day. God bless you all.